started with the recording. And all right. So I think last time we talked about positive exponent in this class. Is that correct? So that's going to be a new assignment, which is kind of stacked upon your other, assignment that's due on Wednesday. So are there any questions about the assignment that is due on Wednesday, which is negative exponent? No questions? Okay. You guys are all comfortable with the tool, online GDB or code blocks or VS Code, whatever you guys want to use. You just have to know how to set the value to be converted. So that's going to be the only part that sometimes I have people asking. So if there are no questions about conversion, from base 10 scientific notation to base 2, which is we call floating point number, but basically they are the same concept. So without any questions about that, we're going to move on to talk about SR latches. But before we do that, let me share with you where we are in this class. So let me go back up. So where we are at this point is we are transitioning to a major different section, which I just called, von Neumann architecture and memory, which is more or less, you know, correct. Um, so the first thing we want to do is to find out, who is von Neumann, John von Neumann, and why is this architecture important, and then talk about, what are the major components in this type of architecture. So we'll get started with an introduction to John von Neumann, and he has a really long page, in Wikipedia. So this is the guy, okay? He, interestingly, I talked to this about the other class too. So he passed away when he was about 54 years old, and I will be 54 years old soon. So I still consider myself not too old. So he could have contributed more to not only computer science if he had lived longer. The father of computer science, Alan Turing, also passed away really early. Some people said that he committed suicide, and then there are conspiracy theory that thinks that he got murdered, by some other people. So anyway, John von Neumann, died from cancer, and some people speculated that he got cancer because he was part of the team that invented the hydrogen bomb. So the guy is very good at many different STEM fields. So the list is right here. Okay, you can see the long list. So he's good at many different subfields of math, computer science, physics, economics, and so on. And if you ask any person in a particular field, about, okay, so what do you think of John von Neumann? Each person, each expert in each field would say that he's a genius. So he's kind of like a super genius in many ways. He also shared his time um, in Princeton with Albert Einstein. And the personality types of these two cannot be more different. Even though they're both geniuses, this guy likes to listen to loud polka music. And you probably imagine what Einstein likes. It's like, shh, shh, no sound. So you can kind of imagine the conversations they have along the hallway. It has to be somewhat entertaining because they're both good. They're both very um, talented scientists, and yet they are also very different. All right. So if you're curious, you can read the rest of this Wikipedia page, which is um, which is fascinating. Okay, I'll just say that it is fascinating. But for us, what exactly is the von Neumann architecture? That is what we are interested in. So for this class, we are really interested in the von Neumann architecture, which has its own page. And this is the von Neumann architecture. You look at this picture and go like, yeah, we kind of know all this stuff pretty much already. I mean, for those of you who have tried to put a computer together, like you're putting a gaming computer together, you already know that, okay, we got a bunch of input devices like the mouse, the keyboard, all the USB devices, right, the hard drive, and so on. And then for the output devices, kind of the same deal. You have your display, you have your speakers and whatnot. So, from your perspective, this is like, yeah, we in the memory unit, of course, we have to install SD-RAM, not SD-RAM, you have solid state drive, but that's the hard drive. That's actually more like an input device. But your memory is more like the DIMMs, DIMMs, the dual inline memory modules that you purchase. You have to match the type, like, oh, is this DDR3, DDR4, or DDR5? How much per stick, and which slots do I populate? In what order? So those are the things that we are kind of used to. But you have to remember, computers did not used to be like this. In other words, if I ask you, okay, you guys are using your laptop computers, using your phone and whatnot. So I'm going to ask you, so how do you keep everything up to date? If Microsoft, found some bugs in Windows, how do you update, Windows? Or if your phone, your apps, have an update, how do you update the apps? Most of you go like, well, most of the time I don't even need to know about it, right? It's over the air. It gets installed, kind of quietly, during the time when I usually do not use the device, and it's all done, right? Well, back in his days, okay, back before von Neumann came up with the whole concept of the von Neumann architecture, if you want to update and change the behavior of a program, of a computer, I shouldn't say program, of the computer, it's all based on hard wiring. You have to physically go to the back panel of a computer, open it up, and it will expose like a bazillion wires, going from everywhere to everywhere else. And then you have to go like, okay, so what do I need to change if I want this program to behave in a different way? So you have to undo a bunch of those wirings and then redo a bunch of wirings. Hopefully, it does what you think it's supposed to do, because if it doesn't, then you have to debug it. You have to find out, okay, which wire did I miss? Or is the actual design, what I was told to do, was that actually incorrect to begin with? And that's because, everything was hardwired. So what do I mean by hard wiring? The 3x3 carry look ahead adder that you guys have done, that's hard wiring. Okay? Which pin from which gate is going to which other pin on which other gate, that cannot be changed. Once you make the circuit, that's pretty much fixed. Is that okay?
It's essentially like almost like an Arduino or like a Raspberry Pi. You know how you have
Yeah.
some of those.
Yep. Yep. But it's about the inside of the chip. Everything is pre-wired and you cannot change it, on the fly. It's like, I don't like the way I'm making this, carry look adder. I think I want to turn it into a subtractor. Okay, I want to put a negation right here. You cannot just say, you cannot do it on the fly. You have to modify the actual wiring. So if you want to look at pictures of how people used to do that, they use a method called wire wrapping, and I'm gonna look for wire wrapping mess and see if I can find some representative pictures of what it looks like. Yeah, I have to look for circuit boards. Yeah, I think this is going to be a pretty good picture of a big mess of wire wrapping. Let me see if I can zoom in a little bit. There we go. Okay. So each pin, okay, each thing, okay, is what we call a pin. And it's pretty long, I would say about an inch long. And then we have these special 30 gauge wires called wire wrapping wire. They are solid core, which means they don't have individual strands. They're a little bit rigid because that's what you need in order to kind of wrap it around the post, okay, and make it secure. So they have these kind of special things called a wire wrapping tool, where you put a fixed length of the exposed end of a wire into it, and then you insert that thing over the post, which is just a metallic um, you know, pin, and then you wrap it. And it will basically wrap the exposed wire, the conductor, around the post. And in some of these, you have a stack of wrapping. So you have one wire wrapped around it first, and then you have another wire wrapped around it next, and you have yet another wire to wrap on top of that. So you can kind of imagine if the bottom one, the first one you wrap around was wrong, you have to undo the other two first to fix the one at the bottom. And this is not uncommon, okay, that people have to do this kind of stuff before the von Neumann architecture. So when Microsoft says, we made an oopsie about the program, the way we specified how the computer is supposed to behave, and you want to update, Windows, you gotta have to open your computer, look at bazillion wires, and find out which one you have to undo, and then reconnect to where, and so on and so forth. It is a mess. Okay. So what did von Neumann said? Von Neumann basically said, well, we already have the concept of computer memory before the von Neumann architecture, except at that time, the RAM or the memory is only used to store the data being processed. Okay, so if you think about calculus, okay, you're trying to do the integration, so you're summing over an entire area, and then you have to calculate the height at a certain point and so on. So all that data is already stored in RAM, in memory, somewhere. So von Neumann just basically said, well, what about we also use that memory to store instructions so that how the computer is supposed to behave is now not dictated by the wiring anymore. It is dictated by the content of memory. If I change the content of memory, which is relatively easier to do compared to changing the wiring, I would be able to change the behavior of the program. So instead of integrating sine from this point to this point, I want to change it so that it's calculating the area under cosine from this point to this point. Using this, you'll be unwrapping a lot of wires, rewrapping a lot of wires. Using the other method, you'll be changing memory locations to change the behavior of the program so that it will be using cosine, and you'll be changing the starting point and also the ending point. Are we doing okay so far in terms of why this is a very important step in the evolution of computers? Because without this, we would not be able to update, how a computer behaves, and that would basically, make the progress, a whole lot slower. Is that okay so far? Okay, excellent. So what we'll do, okay, I'm going to show you a picture of what we are going to do because I want to show you what the processor is going to look like, when we use the von Neumann architecture. So this is what you'll be doing for the rest of this semester. Yeah, I know some of you are thinking for the rest of my life. No, not quite that permanent, just the rest of this class, okay? So you can kind of relax after the end of this class. You may not have to deal with this again, depending on which four-year university you're transferring to. All right, so with this entire thing, this is the memory. Okay, let me point out where the memory is. This is the only one part that is the memory. The rest is actually representing different parts of the processor. Okay, but what is really important here is this this mechanism down below here. This is what I call the microcode engine. And what it does is it will grab locations from memory, decode it, and then find out what the rest of the processor is supposed to do. Oh, you need to connect to here, and you need to connect to here, so that when you're done with this result here, you store that over there, and so on and so forth. Okay? Um, have you guys watched Thomas the Tank Engine?
Yeah.
Some of you have, and some of you have no idea what I'm talking about, right? So, okay, let me show you that picture because I think it is going to be. I mean, these concepts require a little bit of time to sink in, but having an idea of the island of Sodor. I think I might have misspelled it. Nope, I got it. Okay. Hmm?
There's a wiki for that?
Yeah, there's a wiki page for everything, man. Okay. Fictional island. All right, so this is the fictional island of Sodor, which is where the story happened. Okay, Thomas the Tank Engine, along with all his friends. So, why do I bring this up? What does this have anything to do with a processor? So if you look at all the stops, okay, they have stops where there's a factory, there's the dock, where material gets get off of a boat, right? You got factories, you got mines, you have people, stations and whatnot. So in order for this island to operate, okay, to make the things they're supposed to make, everything is mostly, okay, I should say everything, but most transportation is done by trains, okay, engines. So now you have to think about, okay, so how do you run an island like this when you have a lot of trains running around? Some train is supposed to go to the dock to pick up some items and deliver it to the factory, right? And then some other train is supposed to go to the mine and pick up some other raw material and transport that to a foundry, okay, to refine the material. And then from the factory, when everything is done, it needs to transport the finished good to the dock again to be exported. And then you also have to transport the factory workers, right? So every morning you have to go to the major points where people live, get those people onto the train, transport them to go to work, and then at the end of the day you have to transport them back to their homes and so on and so forth. But you only got so many tracks, okay? And so now the question is, how do we make sure that we utilize the tracks, to the point where I can get everything done, but there's no collision on the track? Because it might be the same track that a train needs to go in this direction to transport something, and then later on, or even at the same time, another train needs to use exactly the same track to travel the opposite way to get things done. So now you have to schedule things, right? So to run the tracks, you have switches. Do you guys know what is a switch, in terms of a railroad track? It's a very simple device, okay? So if you want to take a pic, want to know what it looks like, it's a very simple device. So railroad switches. There we go. That's a switch. That's a very typical switch. So basically, you have a mechanism, a mechanical way, so that depending on whether it's merging or whether it's splitting, if it is splitting, then you usually have a mechanical device, so you can just kind of push the lever, and then the train incoming will go to one fork. If you push the lever the other way, then incoming train would go to the other alternative track. Is that okay? So your processor has exactly these things. It has tracks, which are basically wiring, physical wiring between the components. But it also has switches, where you have one input and then there are multiple outputs coming out of it. And you can choose which output is continuing the input. And you can do the opposite, where you have multiple inputs and one single output. Then you can dictate, oh, okay, the output is now connected only to this input. The other inputs kind of have to wait, okay? They can all be sitting there, but they are not passing through. Only one of the input is connecting to the output track. So we have all these analogous structures in the processor. So who is dictating which switch at what time should be configured this way, and then which other switch should be configured the other way, and which train is supposed to leave the station at this point, and which train is supposed to arrive to the other point, and so on.
The command center, I guess, whatever the equivalent of that
Exactly.
would be.
So in the story of Thomas the Tank Engine, who's the guy who's doing it?
It's been years.
Hmm?
It's been years.
I think it's okay. I'm gonna do a search here. So this is Thomas the Tank Engine. I think it's called the Fat Conductor. Sir Topham Hatt. That's it. Okay. So that's his job. Okay. So his job is to sit in an office where he can call up people at all of these places, the train stations, the switches and whatnot, and he gets to call those people at a specific time and go like, okay, I need you to throw the switch from configuration A to configuration B. And then he'll call up the town and go like, okay, you guys can, this train can leave the station now. The tracks are properly configured, so you can now go. And then he'll call up another place and go like, okay, you have to hold that train because the other train is coming this way, so this train kind of have to sit and wait for the other train to get past first, and then you can reconfigure the switch, and then this train can continue. So he is the person who is giving out all of these orders. Are we good so far? That is what's happening in a modern day processor. So what does this have anything to do with the von Neumann architecture? Guess where he is getting his instructions? Memory. Okay? So the configuration of the tracks of the island is not fixed. It can change from one day to another day. Okay? It's a holiday. Nobody is at the factory. Nobody's working. The dock is empty. Nobody's working. Fine. Okay? We'll change the way we run the train. So we'll just be transporting children and whatnot from the towns to the tourist attractions. Do you see what I mean? It is now flexible because this guy is not hardwiring how the trains are supposed to be run. He is reading off of a script, and that script is corresponding to what we see as memory. You can change the script and then change how the island is run. You don't need to go physically go to the tracks and make all the changes. Oh, today is a holiday. We have to lay down a new track from here to here and then take down those tracks over there. Nope. You just change the instructions. You just say, oh, okay, this binder here, that's for work day. This is for a special day. Okay, this is the special day. This is a holiday. I'm going to run the tracks according to this instruction. So we do okay so far with just a general idea of what a processor gets its thing done. Okay, all right. So the very first question, I'm going to close these tabs for now. So what we need to know first is, well, how is memory done? I mean, do you guys ever have the curiosity? Once now that we understand how things are added, right? Because if I need to add these two values, two integers, okay, well, it's not too bad. The first thing is to convert it into a binary representation, right? And then you can choose between signed and unsigned representation depending on whether the value can go negative or not. Okay, so that's the first part. Second part, if I need to add these two things together, what do I do? Oh, we have the carry look ahead adder mechanism. So I can now construct I can configure and or gates, possibly not gates also if you want to do subtraction in a certain way so that if the two inputs are the numbers being added or subtracted, then going through this big mess of circuit, remember the K circuitry, the carry look ahead thing, can be really kind of messy as you try to calculate like K of 20 or K of 63. That can be really messy. But nonetheless, we have a way to do it, right? And then the output of that circuit is like, okay, this binary number here, that is the sum or the difference of the inputs. So we know how to do that already. But what we have not talked about is how does the computer or components of a computer remember something? In other words, we haven't talked about the memory circuit. Okay, how does a memory circuit look like? How can you tell a circuitry go like this bit pattern here? I want you to remember that. Okay, and when I need it back, I'm going to ask you. So how is that done? Okay, that is the first. That's the question that we'll try to answer today. Are there any questions about the context of what we are going to talk about, or the context that we know as the von Neumann architecture? Okay, no questions? Yeah, go ahead.
We're just pretty much dealing with memory, right? That's a big question we're trying to answer.
Yeah, we already know what we are going to use the memory for
Yeah.
is to have so that we can store instructions in the memory. So this way, the instructions can tell the computer what to do, and memory can change. Especially if it is RAM, which is random access memory.
Right.
It is rewritable, so that means if you don't like this program, you erase it and load a new program in, and now the computer can behave entirely differently from what it used to do before.
Right. Okay.
So it'll be easy change. But the question now is, what does memory look like? Because we never talked about the circuitry of memory. We talked about adding, subtracting, and we can use subtraction to do comparison.
Yeah.
So we talked about all of that stuff, but we never really talked about how memory is, how do we construct a circuitry that can perform what we know as memory, what memory does. Okay? So that's the context. So what we'll do is we're going to draw a circuit in LogicSim but we are not going to run it in Logisim. So what we'll do is, let me go back to Logisim first, and then I'm going to use this to create a new circuit. And it's a really, really simple circuit too. So if you go to logic gates, just pick up two NAND gates. I'm going to, let me zoom in first, okay? And it only needs two inputs, so it can be smaller. We don't need to use up that much space. And we need two of these. So now we have two NAND gates, and then we will need two input pins. I'm going to stash one over here, stash another one over here. Two output pins, one output pin to be the output of the first NAND gate, and second one to be the output pin of the second NAND gate. And the wiring is not too exciting. The input goes to the input, the outputs go to the output, the input goes to the input, and then the output goes to the output. You go like, wow, that's not very exciting. Well, you're right, this is not very exciting. But what about this? What about I take the output of one NAND gate and have this output of one NAND gate to go to the input of the other NAND gate? You go like, well, that's still not very exciting because if I draw this picture differently, it will still be going in one single direction, so there's nothing special about this. What if this is, yeah, go ahead.
I don't know. So those are NAND gates, right?
Those are NAND gates. That is
So
correct.
we have zero coming into the NAND gate, and then we have a no input coming into the other side. That is equivalent to having it on. Yes. Is that what it's saying? Because
Well, okay, we'll do the analysis in just a little bit, but
okay,
I think what you're asking is about, why is the output of one when we only know one of the input is a
right,
zero,
yes,
right?
yes.
Okay, that has to do with a truth table. So I will get to the truth table in just a little bit because I want to finish the constructing this circuit here. So this circuit is actually symmetric. In other words, if you were to draw a line from here to here as a mirror, then the two halves of the images are basically exactly the same. It is a top bottom symmetric kind of design. And I claim that this is the smallest memory device when you try to make one out of logic gates. So let me name all the different parts first, and then I'll copy and paste it into a spreadsheet, and then we'll try to analyze what happens when you do certain things with this circuit, okay? And that will address what you asked earlier, which is about why is the output one and blah, 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 okay? So we'll address those questions. All right, so let's go ahead and give these components names. And these names are consistent with what I have also used in the notes. This input pin is called S. This is R. This is N1. N1. And we are still recording, so I would not spend too much time to just to try to copy everything. So it's much more important to focus on the discussion and to ask questions. When you do have those questions. This is Q, and this is NQ, which is basically not Q. That's basically why it's called NQ. So I claim that this, which we call an SR latch, is the smallest memory thing they can construct out of logic gates. But we already know each NAND gate, which two inputs, can be implemented using two P transistors and two N transistors. So we know this entire circuit can be done using 8 transistors, right? 4 P transistors and 4 N transistors, and we can make this happen. So this is physically, we can physically implement this circuit using just 8 transistors. And I claim that this thing has a property of being able to remember something. Are we good so far? Okay. So what I'll do next is going to take a snapshot of this and probably to zoom out a little bit because I think we don't need to zoom in all that much, maybe a little bit like that. So now we'll go ahead and I'll just take a screenshot, okay? And I'll put it into a spreadsheet that is quote unquote prepared for what we are going to do in today's class. So I'm putting it into the clipboard, and this is the last time we need to refer to it, at least for a while. And then I get to this untitled spreadsheet. Let me give it a name first. I will call this SR latch, okay, which is basically just what the name is. And we'll paste the image over here. So this way we don't forget what we are dealing with. Okay. And then we'll try to take a look at what it's going to do. Are we good so far? So let me first explain some terminologies because some of these may not be obvious. The use of an array in input pins is really just to refer to the first versus the second input pin. And then the out is the output of a gate. So N1 and N2 are both logic gates. Each one has two inputs and one single output. And then the SR are input pins, and then the Q and the NQ are output pins. So they only have quote unquote a pin, which is the connection point to talk about. Are we okay so far? Okay, we good? All right. So I'm going to take a second picture because I think this picture does not, I don't want to use it for what we are doing here because I don't want you to have any assumptions about the values at the pins, at all. So I'm going to turn off simulation first thing, and I'm going to reset the simulation. Wait, I have to do one more thing before I do that. This is one of the very few times I want to have a three state as the input pin because I want to specify like I don't know what it is. Okay, so if once an input pin is in three state mode, you can specify a one, a zero, but you can also specify an X, which is basically saying I have no idea what it is. Okay, and then we reset the simulation so everything is unknown at this point because I think this will help with my discussion. So let me do the screenshot one more time and use this image instead of the one that I already had on the other side. So put in the clipboard, switch over to the spreadsheet, take this one out, paste the new one in. Now we can start our analysis. Are we good so far? Okay. So the first thing I'm going to do is I have no idea what the current state of N1 is nor N2. So I'm just going to say they can be anything. I have no idea what they are. Okay. And because the output pins are connected to Q and NQ, I also have no idea what they are. Are we good so far? So the only thing I'm going to say is, well, let's see what happens if S and R are both zeros. Okay. So we'll now say, we'll say this is a zero, and this is also a zero. Okay. Are we good so far? So I'm presenting a low voltage or ground voltage to the input pin S and also the input pin R, so they're both registered as zeros. So the first thing that I need to notice is, okay, how are they wired? Okay, you guys can tell me how S is wired. If I change the input pin S, what is going to change like right away because of the way the wire is set up? How is it connected? The input pin S is connected to N1, but which pin of N1? Because N1 has three pins, two inputs and one output. In zero, correct. Okay, so that's very good. And if you guys prefer me to use color coding and that sort of stuff, I can do that. So let me, I'm just trying to maximize the screen, but it won't let me do that. Okay, maybe it just needs to refresh. 11. Nope, that is weird. Hmm. Okay, how about view and full screen? Does that now? It's just kind of odd. They didn't do it earlier. Um, all right. So now we say, okay, these two are connected. So this pin here, oh, there we go. Okay, now it goes full screen mode, which is good. So these two are connected. So if you want to, I can use some kind of color coding so that they appear, it's obvious that how these two are connected. So I'll just go ahead and use purple for these two. So that means if the S pin is a zero, this pin gets a zero right away. Does that make sense? Because that's just physically how these two are wired. And this pin And this pin, they're also connected because you can see how R is connected to quote unquote second input pin of N2, which is known as in bracket 1. So I'm going to use another color to specify that connectivity. I'm going to use slightly green this time. Okay. So I'm not sure how much the color coding is helping. The best way is really just to look at the wiring to figure out those. All right. So that means if the R pin is a 0, that will immediately change in 1 of N2 to be also a 0. Is that okay? All right. So every time I have no idea what is presented to N1. So because N1 or in 1 of N1, which is this pin, this Y here, is connected to the output of N2. So I can also use a color to represent it. So this, and this, they're all connected. Is that okay? There are 3 points in this particular, what we call a node on the circuit, because they are basically connected by the same conductor. Is that okay? All right. So I'm going to color code it again. And this time I'm going to pick up something on the warm color side, maybe something that is a little bit on the red. And then the other three are also connected. The output of N1 connects to the first input of N2, which is also connected to Q, which is this particular node here. And this time I'll pick a color that is, let's say, yellow, like so. All right. So we good so far? Now, because I said, I have no idea what kind of output N1 and N2 are doing, initially. So that means everything that is in yellow, they will also get a question mark. And then everything that is in red would also get a question mark because this I do not know. I do not make any assumptions. So that means everything that connects to those would also get question marks. So I get basically get a bunch of question marks like so. All right. Do we have any questions at this point of about row 4 of the spreadsheet? That is the current state, okay? In a very in this particular instant of time, as soon as I change the input pins S and R to all zeros, this is what I should be seeing at that very instant of time. Is that okay? All right. So at this particular moment, one thing I noticed is I made some changes to the input pins of some of the gates. In other words, this used to be unknown and now it is known. Okay, well, let's use boldface to represent that. This pin here used to be unknown, now we know what it is. It is also going to be boldfaces, bold-faced. Is that okay? I'm just using boldface to indicate a change because of the current changes to SNR. So technically speaking, you probably want to also boldface both of these pins because they also used to be unknown. And now I say, well, we are just going to specify a 0 for those input pins. Are we doing okay so far with this exercise? All right. So now what do we do? Well, we notice that N1 is a logic gate, and one of its input, at least one of its input pins got changed. So now I have to ask the question of how is the output of N1 going to change, if any, corresponding to this change of one of its input pins? That is the question that I need to ask. Is that okay? Because if a logic gate is trying to perform a particular operation, if you change the input of that particular logic gate, it can potentially change the output of the logic gate. Is that okay? So that is going to take some time. So I'm going to use PD here for propagational delay. Propagational delay. And we'll make it so that it stacks. Or we can always change the font size so it fits. Yeah, let's do that because I only need to refer to the full name once. So after a propagational delay, the output of the gate that has at least one of its input pins changed will now try to say, okay, I got a new output now. Okay. In other words, From the perspective of N1, it basically says before I have no idea what both inputs are, but now I know the first input is now a 0. So now I want to see if I can change the output of N1 to something that is known, or whether it will just continue to be, I have no idea. So how would you answer that question? In other words, if I present this picture to you and say, I know one of the input pins of N1 is a 0, the other one is unknown, can I determine the actual output of the N1 NAND gate? That is the question. What do you guys think?
No,
And why would you say no?
because you don't, it's based on two inputs.
It does have two inputs.
And if you only know one input and you don't know the other output, or that you don't know the second input, then it's inconclusive, right? That's what I would think.
Maybe, maybe not. Okay? Okay, let me ask you, do you remember what is the short-circuited Boolean evaluation property of C and C++?
Shorthand Boolean operation.
It's otherwise known as lazy evaluation of a Boolean expression in C and C++. It's Boolean, right? So it's and or, but it's also short-circuited, which means I'm gonna do the least that I need to do in order to come up with a conclusion. So let me present this to you first, okay? Because this is related, and the more things we try to relate, the more complete the mesh is in our concept map in our brain, in our mind, and then it becomes easier to understand even more concepts as a result. So that's why I want to relate this to as many things as possible. So this way you can basically have multiple pathways in your brain or in your mind to connect the concepts. Okay, so to explain this, I'm going to use Mousepad, which is really just a text editor, because I want to ask you how you would evaluate a certain Boolean expression in C and C++. Okay, so I'm going to present it to you something like this. Okay, x is less than y, and y is less than z. Okay, so obviously this is a Boolean expression. In other words, the and is going to evaluate to either false or true, right? So I'm going to give you a few scenarios. I will ask you, what if x equals to 0, y equals to 1, and then z equals to 2? Okay, it should return true, and that's because x is less than y, right? But just knowing one side of the and is true, is it conclusive to say the entire conjunction is true? No, because the second one can still mess it up, right? So in this case, we do have to evaluate x is less than y and also y is less than z. Okay, we have to evaluate both to conclude the answer is true. Okay, all right, not a bad deal. What if x equals to 2 and y equals to 1 and z equals to 0? So now you look at this, expression, you go like, okay, well, we're going to read from left to right. And this is also guaranteed in all C compiler, is when you have a logical operator like and or, it is guaranteed to evaluate from left to right. Such a guarantee is not made when you have multiplication or division. The compiler can go like, well, I can always evaluate things in any order I want, as long as I get the multiplication done, as long as I get the division done. You really should not care about the ordering of whether I got the right hand side first or the left hand side first. But in logical operators, it is always guaranteed that the left operand is evaluated first, and if necessary, the right operand will evaluate. So in this case, if I already know 2 is not less than 1, that means one side of the and is a false already. Do I need to evaluate the right-hand side?
No.
I don't, right? All right. So let me just make this, write it down. Okay, so this one only has to evaluate x is less than y, then conclude that the answer is false. Does that make sense to you? Now, it doesn't hurt to evaluate the other side, but do I have to? Nope, I don't have to.
I think I see what you're trying to get at because a NAND, because if one of them's one, then it's going to be true, correct?
If one of them is a zero, then the NAND is guaranteed to be true.
Yeah.
All right, this has to do with the truth table as well. So if you look at the truth table of NAND, you have x, y as independent variables, and then you look at x. Okay, I'm going to spell out x and y, like so. So x can be false, then the whole thing is going to be true. X can be false, y can be true, the whole thing is still true. X can be true, y can be false, the whole thing is still true. It's only when both are true then the entire thing is false. We have seen this truth table already on the first day of the semester. You go like, wow, that was a long time ago. Are you expected to remember from something that far back? The answer is sort of. You should be able to at least recall that we talked about it, okay? Whether you have the exact truth table actually memorized, no, I don't think so, because it's open book and open notes. You can always look it up. Okay, so how is this truth table going to help us, in to answer the question that I had earlier, which is in the spreadsheet. So in the spreadsheet, okay, I'm trying to answer this question. It's like I only know one side of the NAND gate is a zero, but can I conclude the output at this point? So what you do is you go back to the truth table and you go like, okay, so I'm looking at these two rows, okay? I'm looking at the output of the entire thing. Hey, it doesn't seem to depend on y. Let me highlight the two rows that we are considering right now. You look at these two rows, they both have x being false, right? But what about the expression, the result of the entire expression? They're both true. So it would seem to me that y, whether y is a 0 or 1, doesn't seem to matter. Is that okay? So that means when we switch back to the spreadsheet, we can also now conclude and say, well, it's going to be a 1, even though we don't know what the other input is, because one input is a 0, I can guarantee the output of this NAND gate to be a 1 already. Is that okay? All right. So I can say the same thing. Oops, sorry, pressed the wrong key. And I can say the same thing about the output of N2 because I also know one input, which in this case is the second input of N2, is also a 0, which also guarantees the output of N2 being a 1. Okay, wow, that is cool. But since NQ connects to the output of N2, that is going to be a 1. And since Q connects to the output of N1, that's also going to be a 1. But since N in 0 of N2 also connects to the output of N1, that's also going to be a 1. And since N in 1 of N1 connects to the output of N2, that is also going to be a 1. I have just resolved every single pin or every single unknown at this point. Is that okay? But remember, I also need to note the changes, okay? What just got changed this time? A bunch of stuff, right? This got changed, 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 this got changed. This is going to stay the same as a 0, so it's not going to be boldface. These were zeros and they continue to be zeros. Is that okay? So at this instant of time, which is after a very small propagational delay from the previous row, both outputs are now ones. Is that okay? But every time I change one of the input pins of something, I have to ask the question, is that going to change the output? I just changed a bunch of input pins, right? Because this change is corresponding to an input change. This change here is also corresponding to an input pin. So I have to re-ask that question. So once again, after a certain propagational delay, I have to ask, is this change going to affect the output of N1? Well, the answer is no, because I still have at least one of the input pins being a 0. So this is continuing to be a 1. And then I ask the other question, is the output pin of N2 going to be changed because the first input pin of N2 just got changed from an unknown to a 1? The answer is no. N2 will continue to output a 0, will continue to output a 1 because the other input pin of N2 is still a 0. So I got a 1 here again. And once again, they're not bold-faced anymore because it's not a change. It used to be a 1. It continues to be a 1. And nothing else is changed. Okay, so all of the other columns remain the same as the previous one. So when you see that two rows between two rows that they have identical values, then you basically say, yep, I think we have arrived at a what we call a steady state, which means I don't need to track changes anymore. Nothing is going to cause any additional changes. Is that okay? All right. So now we're going to do something that's going to be fun. Excuse me. So what we'll do now is to take this as the input of another step of using this particular circuit. Okay, so this is going to be the starting point. I'm going to say starting point. And this time I'm going to change one of the input pins from a 0 to a 1. You guys can choose, okay? Out of the two input pins, S and R, which one do you want me to change to a 1? It doesn't really matter.
Change that.
Go ahead, R. R? Okay, you guys.
We'll change R.
Okay, change R.
It's
Okay.
arbitrary.
Yeah, it's really arbitrary because the circuit is up down symmetric. So the behavior of changing the other one is going to be the same, except the top becomes the bottom. Okay, so we're going to change R to 1 like that. And this is a significant change because we just changed it. It used to be 0, now it is a 1. Is that okay? And because all the green stuff are connected together, so that means this got changed too. Is that okay? So now we also boldface this one. And then that's it for this point here. Okay, so this is change, input change. The rest stays the same. Okay, so nothing else is getting changed at this point. So after a propagational delay, okay, so this is very important to understand that there is a delay between row 10 and row 11 because row 10 says, hey, for input pin, okay, which one got changed? This one, which is causing this one to change. So the second input pin of N2 just got changed. So if the at least one input of a logic gate is changed, we have to question and ask, is that going to change the output? Right? But that change of the output occurs after a certain delay, simply because it takes time for the transistors to change the way they behave, connecting and not connecting a circuit. It takes time from the moment the gate pin is changed to the moment that it allows or disallows current to pass through. Is that okay? It's just like a relay, right? A relay is very slow because from the moment you say, I want this input of this relay to be a 1, it takes time to energize the magnet, right? And then when the magnet, after the magnet is energized, it takes time because of physics, thanks to Newton, right? It takes time for the contact point to move from one contact to the other side of the contact. There's a certain delay. A transistor is a whole lot faster, but it doesn't mean it's instantaneous, except it's just that the delay is a lot shorter. There's still a delay that we call the propagational delay. Is that okay? So now the question is, okay, let me just put the question marks here. It's like, um, if this input pin is changed, what about this output pin? Is it going to change as a result? So let's try to figure it out. Okay, so now we are trying to figure out N2, what the output of N2 is supposed to be after the change of at least one input of N2. What do you think? Remember the truth table that we displayed earlier?
It will change.
It will change to
False.
False. Very good. Okay. So this is changing to a false. So because it's a change from a 1, I'm going to highlight it. But when you change the output of N2, two other pins are going to change. Two other connection points are going to change. Can someone tell me which other 2 points are going to change as well? N in 1 of N1, yes, that is going to change from a 1 to a 0 as well. And we're looking at all the red thing.
And then, so in Q,
Yep.
the output pin is going to
Yep.
change to 1.
Exactly. Yep. So all of these are changed.
This is false.
Yep. Changed to a false. That is correct. All right. The rest of the circuit, everything else, stay the same. Okay. So we just have to say, well, that used to be a 0. That used to be a 1, 0, 1, 1, 1, and then a 1. Okay. So now you look at row 11, and then you ask on row 11, which input just got changed? The output pin says, oh, don't look at me. I'm the final terminal here. I can change all day long, but it's not going to change anyone from within the circuit, so we don't have to worry about that. You look at column, you look at column I, well, that got changed, but it's an output pin of a gate. So that's what started the change of the other things. So I'm not too concerned about that. But then you look at column E, you go like, oh, we just changed one of the inputs of another gate. So maybe we should take a look at this and see whether it's going to cause problems, whether it will start another change. So now we look at this, the output of the gate, where one of its input pins just got changed, which is the output of N1. And then we ask, what is the new output of N1 at this point? Well, did it change? If it didn't change, then we go like, oh, okay, we're done here. But if it did change, then we have to continue to track the changes. So the question is, what is the output of N1 when both inputs are zeros at this point? Think about, exactly, it is a 1. So if it's a 1, is that a change from what it used to be? Nope. So I'm not going to use boldface because now we have, it's not a change. All right, nothing else got affected, right? This is the end of what we call the change propagation because at this point we made some changes, but now we have arrived to a point where, oh, okay, that change did not trigger another change as a result. So now once again we have reached what we call a steady state. Okay, we have now reached a steady state, which means everything else get to see get to be the same as before because we are no longer making any additional changes. So the analysis of this thing is now done. Okay, we are done with this analysis. Are we doing okay so far with this analysis? We are basically analyzing if I change the input of this thing here after a certain delay, is it going to change the output of that thing? We are just tracking those changes at this point. Is that okay? So this type of reasoning is dependency based. This thing depends on those things. One of those things depends on those things. So if I need to figure out whether something's got changed, I have to look at the dependency. Is that okay? All right. So I'm gonna make another thing here. I'm gonna take the final output of this particular step and go like, okay, we'll use this as a starting point of another step. Okay, except this time I'm changing S also from a 0 to a 1. This is my change. Everything else stays the same as last time. Okay, so we got the 1, you got a 0, 0, 1, 1, 1, 0, 1, 0 here. And I can make this a lot easier to read. Let me just kind of propose a way to use a spreadsheet. So this way I can scroll one portion without affecting the other portion. So you can see how you don't have to skip a bunch of rows to get to the one that we are actively trying to work with. All right. So this is my input change, And this is the first change. Then you go like, wait, hold on a second here, Tack, you forgot about something because all the purple stuff are connected. So that means this is also going to be changed from a 0 to a 1. We should make it a both phase. So now you look at row 16 and you ask the question of, did I just change one of the input pins of something? What do you guys think? Yeah, column N1, excuse me, column D is corresponding to the first input of N1. Yes, so we did change the input of one of the logic gates, which means, okay, so we have to wait for the logic gate to finish its job, which is a propagational delay, and then we have to look at the logic gate where one of the inputs has changed, and that's going to be, so now we have to focus on the output of N1. So what do you think is the output of N1 at this point, based on what we know about the NAND gate?
It's true.
It is continuing to be a true. It's not changing. Wow, okay, so even though one of the input pins got changed, but the output continues to be a 1, which means, oh, once again, we have arrived at a steady state where no additional changes is expected. Are we okay so far? Are we good? Okay. So now I'm going to go all the way back to answer your question of, but what if we change the S pin earlier from a 0 to a 1 instead of R changing from a 0 to a 1? So now we're going to address that particular question. All right?
Before we did R.
Yeah, before we did the rest. Before we change both input pins, to a 1. Okay? So now we are going to take a look at, we just basically copy the same starting point from here. And I'm going to stash it over here. And this time, this is my starting point again. And then the input change is to change the S pin from a 0 to a 1. And then everything else should remain the same. So let me scroll up again because this way it is easier for us to match the description of the pins. All right, so if this is changed to a 1 first, then this is going to change to a 1. So both of these should be bold-faced because they are changes. But everything else stays the same because my change is limited to only one pin at a time. And one of you is going to be thinking, so what if you change both at the same time? We'll address that fun scenario next. Okay, so are we good so far? I just changed input pin S from a 0 to a 1, but because of how the circuit is connecting the components, the first input of N1 is going to get changed also instantaneously. All right? So now we go through the same analysis, okay, the same boring stuff, because at this point it should be somewhat boring, but let's do it one more time, right? So this is an input pin. It's corresponding to in 0 of N1. So that means I really should be asking whether the output is changed as a result. So what do you think? Is the output of N1 going to change because the first pin of N1 just got changed from a 0 to a 1?
Yes.
And how, well, I mean, this is a,
It's going to change from true to false.
it's going to change to
False.
false. Very good. So change from true to false. We're going to highlight it. And then all the yellow stuff should also become zeros, right? Because they are connected in the circuit. So all of these are going to be bold-faced to indicate that they just got changed. But everything else will remain the same. So we still have a 1, 0, 1, 1, and then a 0, and 1, and a 1 over here. Is that okay? So now we look at row 22, and then we ask the same question. Did we just change one of the input pins of one of the gates?
Yes.
Yeah, we did. Sure. So this time it is in 0 of N2. So N2 may change its output as a result. So now, once again, we have to wait for a certain propagational delay. And then we ask, okay, since we just changed the first input of N2, is that going to change the output of the same gate? So now we have to answer that question. What do you guys think? Both inputs of N2 are now zeros. It's going to be the same. Very good. Okay, so it's going to be the same, so I'm not going to bold face it. and everything else, oops, sorry, I just clicked the wrong key. And then everything else should remain the same except for, yeah, everything was remain the same because we are not experiencing any changes in this case. That's a 0 and that is a 1. Are we doing okay so far? And then we'll do that one more thing. Okay, the last thing is to change the remaining input pin, which is R in this case, to a 1. Okay, and then some of you guys are thinking, this has got to be one of the most boring class of the entire semester because we just did that. Tag, did you forget? No, I did not forget, but we're going to do it. Okay, so we are going to take the final state, the steady state of the previous step, copy that over here, and say, well, this is going to be my starting point of another step. So in this case, my input change is to change the other input pin, which is R, from a 0 to a 1. And we've got to boldface that. Locate everything that is green because they're all going to be changed at the same time because of the way they're connected in the circuit. And then everything else would remain the same as last time, as before. So everything else is just a copy of what they used to be. So, and now the question is, if you look at row 27, what is the question you should be asking at this point? You just changed something.
What input is changed?
What input is changed? In other words, which gate may potentially change its output as a result. So looking at the bold phase, I'm not sure how obvious it is to you guys, which logic gate may change its output as a result? We only got two gates, which is N1 and N2. So which one is the one that might get changed because of one of its input pins getting changed?
N2.
N2, very good. So now our focus is going to be the output of N2, which is right here. And you tell me, I mean, is it supposed to change? Let me scroll a little bit so it's easier to read. It should not change because from the perspective of N2, even though one input pin went from a 0 to a 1, oops, okay, let me, no, don't do this. Undo, there we go. So even though one of this input pin got changed from a zero to a 1, the other one remained to be 0. So that means the output of N2 continues to be a 1. And this is the only logic gate that can potentially have a change. So that means if it's not changing its output, nothing else is going to get changed after this propagational delay. So I still have to say after a propagational delay, everything is now in a steady state. And you go like, but tech, we have done this before. What is the big deal of this, right? So I want you to compare the two, which is row 17 and row 28, because both of these have both input pins, S and R being ones, right? And then you look at the output pins. I don't really care too much about what is inside the circuitry at this point. I just want to look at the output pins. This one has the output pin Q being a 1. Oh, this one has the exact opposite. What just happened? Isn't that fascinating? The same inputs no longer result in the same outputs because of an intermediate step in between. Okay, first of all, do you guys understand what I'm trying to, what is the point that I'm trying to make?
It has to do with memory, right?
It is memory. It's remembering something.
The order matters, I guess.
The order matters, and when we change only one of the input pins, that is how you set the memory. When one of the input pin is a 0 and the other one is a 1, that is how you specify what this thing is supposed to remember. When both input pins are 1s, then you're basically telling the device to go like, just maintain that memory. Maintain what you had. Because you can see how you're changing R from a 0 to a 1 did not change anything as far as the output pins are concerned. And it did not change before either. Let me scroll back up so I can show up. Okay, come on. Let me scroll back up and I can show you the same thing. This is after we change one of the input. So this is after we make one of the input pins a 0, the other one a 1. And this is after we change the remaining 0 to a 1. And you can see how the output pins are basically just maintained. This is the memory effect of an SR latch. Is that okay? Let me see if I can summarize, what the configuration of the pins are doing. Okay, so I'm going to use a truth table. I'm going to use the text editor for the truth table here. Okay, so SR latch truth table. So we are not looking at the circuitry anymore. We are simply looking at the input pins, SR. We're looking at Q and Q as the output pins. So we know that if both are zeros, Q is going to be a 1 and Q is going to be a 1. That's the first step that we did. We know that if one is a 0, the other one is a 1. In this particular case, what was the output? We got this as a 1 and that as a 0. I mean, you guys can check the spreadsheet and make sure that I did not misquote, but I'm pretty sure that is the case. On the other hand, if you make as the input pin as a 1 and the input pin are a 0, then it's going to be exactly the opposite. Q becomes a 0 and an NQ becomes a 1. What is interesting is what are you going to say about when both input pins are ones? So
Whatever it was coming in.
yep, they call NC, which stands for no change. In other words, when the input pins are both ones, Q just maintain what it used to be, and Q just maintain what it used to be.
It almost falls the truth table above it in a weird way.
It does. This is the summary of the truth table that we saw earlier. So this NC, no change, that is another word of saying remember. Okay? As I said that word in my mind, in my kind of really distracted and always busy mind, Spock came to the screen. In what was the movie? Um, when he was about to die and he was on one side of the glass, he was getting radiation poisoning, and then um, Bones, was there, and then trying to save him, and then Spock, did a mind meld thing and just said, remember. And Bones thought, that was just meant to say, I'm your good friend, do not let me die without remembering me. But he actually meant something else. Spock actually transferred part of his consciousness into Bones' mind to preserve his quote unquote self. Okay, never mind. If you're not getting it, watch more Star Trek movies. Not a track guy. But anyway, NC means maintain memory, maintain what it used to be. Okay? So there's one transition that we haven't looked into. Okay, I'm looking at the time, it's like, we are running out of time to talk about that. We can make it an exercise. Okay? So I will set this up and then we'll talk about that next time. But I want you guys to be able to try to run it through first, okay? Because this is the fun thing. So what we'll do is we're going to go back to what the result after setting both input pins to zeros. So we're taking this row, and then we say start with that. Okay, this is my new starting point. Starting point. But this time I'm going to make the input change as this. This is my input change. Okay, I will boldface both of these because they are in fact changes. But I want you to finish this analysis until you get to a steady state, until you say, I'm not really sure what's happening here. I will just wait until the next class meeting.
My guess without doing it is it's just going to continuously change. back and forth.
Yes, you're correct. It goes into what we call an oscillation. So it goes into an oscillation with no further changes to the input pins S and R. The rest of the circuit will go like that. After each propagational delay, it flips. Okay? But I want you to kind of go through the analysis like what we did today, okay? Row by row, okay? For each row, if one output changes, figure out all the other things that are connected to the same node, change all of them, and then you analyze, is one of those things the input pins of something? If it is, then you have to start the next row and say, did that change the output of the gate where the input just got changed? So you need to do that analysis, but this time is going to be more entertaining because you will see that there's no steady state in this case. You basically start the circuit into an oscillation. So it just be the output is just going to be ones, zeros, ones, zeros, ones, zeros, and it'll keep on going forever. Okay? So now that you know what it is supposed to do, I still want you to do it because the exercise of doing this is beneficial to the next exam. It's not so much that you're memorizing the tables, it is you understanding what is involved as you go through the analysis. All right, so we are out of time for today's lecture. I'm giving you the new assignment, so let me show you what I just released for today's lab. Oh, okay, back to so I just released positive exponent, which is the opposite of negative exponent. And when you look at the assignment, it's set up pretty much the same way, except your exponent in base 10 is going to be positive. So this time I also give you a trace of what if you use 1.2345678 times 10 to the power 30 as the number being converted from base 10. And these are the values that you should start with. The exponent, the coefficient should be 1, 2, 3, 4, 5, 6, 7, 8, 9 as one single integer. The exponent of 10 should start with 22. The exponent of 2 should be 0. And then the next step is to make the mantissa as large as possible because you can afford to, because you can see how your exp10 is 22 and now it is 11. Unfortunately, this is the largest you can make the coefficient, within the range of a 64-bit unsigned integer. So at that point, you need to make room for another division by 10. To do that, you have to basically divide this. Okay, after you divide this number by 8, then it becomes this particular number. But because you're dividing by 8, you also have to increase the exponent of 2 by 3, and then you perform a division by 10. After the division by 10, you end up with this number. Excuse me, after multiplication by 10, I take it back. After multiplication by 10, you end up with this number, which is also just barely fitting into a 64-bit unsigned integer. But because you multiply the coefficient by 10, you have to decrease one from the exponent of 10 without changing the exponent of 2. But now you have to divide it again by a few times, this time 4 times. So if you divide this number by 2 4 times, which effectively is division by 16, you end up with this particular value, which has enough room for another multiplication by 10. You perform another multiplication by 10, which now has a number that is barely fitting into 64 bits. But because of the multiplication by 10, you have to decrement exponent of 10 by 1. And each time you divide a number by 2, you have to increase the exponent of 2 by 1. So that's basically giving you a blow by blow by blow snapshots of how the values should change in the structure that Pn is pointing to as your algorithm go through the logic. Okay, that was a sentence to construct in my head on the fly as I say it. that okay? So this will give you a point of debugging your code. If you use exactly the same starting point at this code here and put a breakpoint at the end of each loop, you should be able to verify whether your logic is following what is displayed here or not. Is that okay? All right. So that's that. I don't have anything structured for the lab time for today because I want you guys to kind of continue to focus on finishing up the negative exponent assignment. And also, if that is done, you can get started with this one. So you guys can stay here to work on the program and ask me questions if you have any, or you can move on to some other lab because if you think you can continue to do this on your own, that's fine too. I do want to say that I have started to grade exam one. So some of you got a score already. Some of you may not have gotten the score because I'm only kind of halfway through this class. So that should be done sometime tomorrow. So after tomorrow, the entire class should get your score, at least your raw score for exam one. All right. Any questions? Any questions about exam one? Okay. All right. So I will stop the recording and you guys can stay here and ask me questions, or you can go to